Physics and engineering are two very common toss-ups for students, including myself when I was in high school. Maybe you've taken a high school physics course, liked it a lot, but don't know if that directly is the best route versus engineering, since engineers of course use physics on top of engineering principles to solve problems. Well, I'm going to lay out the differences between each major, the pros and cons of both, and what your options are, then hopefully you can make an informed decision. If you have not seen the physics video I made, I recommend you do that before this because I left a lot of the more technical information out of this one so it would not be too repetitive. I will repeat some things though in case you are going to go through this video first. Before anything, let's start with the pros and cons of each major, because based on how long you want to be in school or what options you want afterwards, this may push you in one direction. One pro of engineering is that it has a more direct career path. If you study mechanical engineering, you would apply for mechanical engineering related jobs with a title related to what you studied. As I'll talk about soon, a lot of people who study physics don't work in physics jobs. Then you only need a bachelor's degree for most engineering majors, and you can definitely be making pretty good money right after graduation. If you want, you could go right into the workforce, find a full-time job that allows you to support yourself, and work your way up from there. Physics, on the other hand, opens you up to a wide range of job sectors. So does engineering, but if you look at the stats, you'll find physics graduates with bachelors ending up in engineering roles, software developer roles, finance positions, as teachers, and so on. It might not be the best direct path to an engineering job, for example, but it totally happens. You also gain a lot of foundations as a physics major in terms of the various branches within the field. You learn concepts from the ground up, such as thermodynamics, classical physics, quantum physics, etc. And if you decide to do engineering afterwards as a master's, let's say, your technical background will be advantageous and accelerate your ability to grasp engineering theory. The main con of physics is that in most cases, you need a PhD to work as a physicist. You want to work in astrophysics, string theory, high energy laser research, work with particle accelerators, relativity, work on quantum computers, etc., and perform the role of a physics researcher in those fields, you really need a PhD. If you just want to go to college for 4 years and jump into the workforce, maybe engineering is better for you, but again, not required. If you are willing to be in school for probably 8 to 10 years after high school, in which you'll do 4 or 5 years of a bachelor's, then likely 4 to 7 years of a master's and or PhD, so you can work as a researcher in physics, then of course starting with a physics bachelor's is a good place to be. And the other con of physics is the career path isn't as defined. Even if you do a physics PhD because you want to work as an astrophysics researcher at MIT or another big research school, there aren't enough spots for everyone. You may end up at a tech company instead, maybe as a data scientist, at a defense company, and so on. Nothing wrong with those at all either. It's very likely you will find a job you like, but keep your options open in case it's not exactly that one thing you wanted to do. Now for cons of engineering, I've seen people post several that are more specific to them. In general terms, the only thing I could really think of, which is more on the topic of getting a bachelor's, is you might not start with the most exciting work, which really applies to physics bachelors as well. Some people work for companies that do cool things, but they start with very basic assignments that aren't exactly the advanced research or design work you may want to do. I mean, maybe you will start with that. There's no way to predict what your career will entail to begin, but in most cases, you got to work your way up to your dream job. You won't start there. Now, there is overlap in what you can do in both of these fields, but I'm going to list some careers that might be more geared towards engineers and then some geared towards those physics PhD positions. If you have an interest in designing bridges, tunnels, dams, roads, buildings that can stand up to earthquakes, etc., then civil engineering might be good for you. Aerospace engineers can work on the structure of an air or spacecraft, design and test the propulsion system, ensure that an aircraft is capable of traveling at supersonic speeds, analyze the aerodynamics, and so on. Electrical engineers can help improve the efficiency and speed of electronic systems, like those in your phone and computer, all the way to those in satellites. You can work on wireless communications and ensure that two satellites can communicate with each other securely, or you could help improve the coverage for a cell phone company. You could work on solar panels, power systems, and more. Chemical engineers can work on chemical reactors, control systems, safety systems, and more for places like Procter & Gamble or Budweiser, where large chemical reactions take place and everything must be handled very properly. Chemical engineers work on the process that makes solar panels, computer chips, food and drinks, medicine, rocket fuel, and so on. Mechanical engineers can work on cars, including the engine, structure, suspension, and braking. They can work on aircrafts, robotics, maintaining a proper temperature within a spacecraft. They can help make wind turbines that are aerodynamic and highly efficient. There are submarines, roller coasters, biomedical equipment, and so much more. This is one of the most broad engineering disciplines there is. Engineers write software, build control systems, develop ways to help the environment, design medical tools, power plants, renewable energy technologies, and plenty more. I could honestly keep going for a while, but note that engineers are not the only ones who work on these, and physics majors could get into several of these fields. However, in general, a lot of these are more geared towards engineers, and if any of them interest you, engineering might be a better major. Especially from a research perspective, you will see physicists in these positions, like improving the speed of computer chips, for example, but again, most of these are classic engineering examples. Now, engineering has all these branches, but if you study physics, you'll likely start simply as a physics major, where you'll learn foundations of various branches of physics. However, when you go to grad school, there are many fields for you to get into that can lead to different areas of research. An astrophysicist or cosmologist may study black holes, galaxies, supernovas, the cosmic microwave background, dark energy and why the universe is accelerating, etc. A plasma physicist may work on research in fusion energy, which is the process that powers stars like the sun, which we want to use here on Earth to power our homes and businesses. They can work on ion thruster research, which is a form of electric propulsion for spacecrafts. Then a very common but not well understood phenomena that exists in the universe is something called magnetic reconnection, which is when magnetic field lines within a plasma break and quickly reconnect. As an example of research, Princeton has a magnetic reconnection experiment in which they generate and study these reconnections under lab conditions in order to teach us more about solar flares, auroras, and more. A condensed matter physicist can do research in superconductors or conductors with no electrical resistance. These currently only exist at very cold temperatures, but if we can create ones at room temperature, there would be countless applications, including faster computers, very accurate sensors, all the way to cars that can hover above the ground. Then one specific area of research is spintronics, which is about manipulating electron spin in order to produce certain results. Because electrons are charged, this spin gives electrons the properties of magnets. Current research is mostly about using that spin as a carrier of information, so we can represent data by the direction of that spin instead of physically moving charge or current. Some of this research has led to electronics with enhanced memory, reduced power consumption, and more. These physicists could work on lasers and nanotechnology as well, just to name a few fields. This is a big branch as it deals with the macroscopic and microscopic properties of matter. Particle physicists are the ones working with particle accelerators and trying to understand physics beyond the standard model. This model classifies the known elementary particles, which are not made up of anything else, and also describes 3 of the 4 fundamental forces. The gravitational force is the big missing piece to this puzzle that the model does not explain, at least yet. The standard model is a great low energy approximation, but is not valid at higher energies where gravity cannot be ignored like it can for small particles. The theoretical math behind including gravity in this model leads to infinities that we cannot make sense of currently. And experimentally, we would ideally like to detect a graviton, a hypothetical particle responsible for the gravitational force that we would include in the standard model. But we have never detected one, and we know that doing so would be very, very difficult. Physicists are hard at work trying to piece this all together, though. Particle physicists are also looking to explain things like the nature of dark matter and dark energy, which are 2 topics we know very little about, dealing with the movement of galaxies and the expansion of the universe. Particle physicists are also trying to determine the mass of a neutrino, which once was thought to be massless, but now we know is not. The question of what their mass is still remains. They're exploring the origin of mass, structure of a proton, the nature of hot and dense matter of the early universe, and plenty more. And of course there are a lot more subfields, but these are just some of the unique areas of research you can get into, and you can see their popularity here. Now, like I said in the physics video, a lot of these jobs lie in academia, where you do research for a university in your field of expertise and work as a professor as well. Or a good amount of these jobs can be found at national labs or government agencies, where you do a lot of experimental physics-related research. If you don't want a job in academia, physicists can of course get research jobs in industry where you'd work for a company such as Google, Boeing, Microsoft, etc., who hire physics PhDs. These are where you could work on laser technology, high-speed circuits, quantum computers, and so on. This research is more often for the purpose of making a product for that company rather than determining the physics of black holes, for example. Next, I want to show a little about the differences in the curriculum for both physics and engineering. There are of course way too many engineering disciplines to go over everything, but I will talk about classes that are similar and also how they differ. 2 of the most famous engineering classes that most engineers take are statics and dynamics. Statics is basically a physics class on systems that are not moving. Examples from a textbook would be like some network of pipes or a bridge/truss. Nothing is moving in these systems, so you'd be asked to find the force or torque at various locations within the system so you can see what one beam, let's say, feels and which way it wants to move. A dynamics class would be about systems that are moving. Examples of problems would be like some complex pendulum that swings back and forth. This problem specifically asks the maximum angular acceleration so the crate does not slip given some coefficient of friction. Or you might have some system with a lot of moving components where you'd be asked to find the velocity of a certain beam based on given information. These classes are all about classical systems, nothing on an atomic scale or anything like that. And they involve plenty of math, vectors, calculus, etc. But they are a little more on the engineering side. Physics majors, on the other hand, take a class called classical mechanics, which is again all about macroscopic systems, projectiles, etc. So what's the difference? Well, in this class, at least at most colleges, they learn more about the underlying math behind macroscopic systems and solve more general physics problems from there. If you've seen my physics video, you know they learn about Lagrange's and Hamilton's equations, which give you a lot of power in terms of representing complex systems. Directly from a textbook, you could be given a problem in which a mass slides down a circular wedge. For people who have some basic physics knowledge, this may seem easy. But in this problem, there is no friction on the wedge or the ground, and you'd be asked to find the equations of motion for both the mass and the wedge itself. Here's the answer, by the way, to emphasize the complexity compared to what you may think. Or you could be given some complex oscillating system in which you need to determine the equations of motion. So there is some overlap for physics majors and engineers in terms of the types of questions, whether it be an oscillating system like this one, a center of mass problem, and so on. But a physics major will usually derive equations of motion from the ground up and deal with a more broad range of physical systems, whereas engineers use a lot of already known concepts to deal with complex systems. Yes, I am generalizing a bit here, but hopefully you get the idea. Another huge class for certain engineering disciplines is thermodynamics, whereas physics majors take a class on thermal physics, often called statistical mechanics. While they of course both deal with heat and temperature, how they relate to energy, etc., a thermodynamics class is more about the practical applications, whereas thermal physics covers more of the underlying science. A thermodynamics class would involve problems dealing with heat exchangers and turbines where you might have to determine the net power developed. There would be various problems dealing with engines or aircraft propulsion systems, you'll learn about refrigeration cycles, and more. A thermal physics class would have more general problems, such as estimate the probability that a certain volume within a room becomes devoid of air. Or you could be asked to find the equations of state for two different types of ideal gases in the limit of high temperatures. I mentioned before how when you cool a certain class of particles called bosons to near absolute zero, you obtain something called a Bose-Einstein condensate, which some people call the fifth state of matter, and is also a topic of interest in thermal physics. So you see how it's a little more broad and less on the practical side than an engineering class. These thermal physics courses, which you can take a few of in undergrad, go into way more depth than what I've talked about though. Honestly, I had to do a bit of searching to find problems that would be generally understood by the audience. Most questions within the thermal physics textbook were a bit more complicated and math heavy, but this is nothing you need to worry about now. So as you can see, there are differences, but both engineers and physicists learn a lot of the same basics. You gotta learn entropy, the laws of thermodynamics, basic equations, and so on. If you flip through these textbooks though, you would notice a difference in topics, and also how the physics side of things is a bit more math intensive. Another overlap between physicists and engineers is electromagnetism, which is really something that electrical engineers of all engineering disciplines mainly take. There is a lot of overlap in these classes where you learn the equations that govern electromagnetic waves, which make it so we can talk on the phone, listen to the radio, and so on. Both majors learn about waveguides, which allow these waves to travel a certain path to a receiver or electrical system with minimal loss of energy. When I was working on satellites at my first job, these were the things that were carrying the wireless signal from the receiving antenna to the computer for analysis, so they are used a lot in high-frequency systems. Electrical engineers would have a lab for this class in a lot of cases though, where you'd analyze how very high-frequency signals behave when traveling through special cables. When you have voltage and currents oscillating in a cable billions of times per second, a lot happens, and in a lab electrical engineers would analyze these effects such as reflection, transmission, and so on. A physics major will learn more of the theory, but may go beyond engineering applications such as relativistic electromagnetism, how these waves would appear to observers moving close to the speed of light. Physics majors then also take a circuit/electronics class where you learn a lot of circuit components and circuit analysis. This will likely be like learning 2 or 3 electrical engineering courses all in one, but you'll go into much less depth. And lastly, there's a physics course called quantum mechanics, which is huge for physics majors, and they do take a few of them. But electrical engineers and often computer engineers will take one as well, but just one. The reason is because some of the topics in that class can be applied to how electrons and atoms behave within transistors, one of the key electrical components within your electronics. Electrical and computer engineers learn a little about the chemistry and physics of these circuit components in their semiconductor course, which requires some quantum physics knowledge. But then they go on to do actual circuit analysis with them instead of diving into the upper division quantum mechanics material like physics majors do. Now these are some of the similarities, but honestly there are many more differences in physics and engineering curricula than similarities. To name just a couple, aerospace engineers take a course specifically on aircraft or spacecraft propulsion systems, or one on supersonic aerodynamics. Electrical engineers take classes on power systems or signals. Civil engineers take courses on reinforced concrete design, or take courses on seismic principles and how to make structures earthquake resistant. And computer engineers take courses on microprocessors, the central processing unit, and more. And that's just a few examples of courses that physics majors won't take. So overall, yes, if you look at any engineering flowchart, you'd see only a few classes that overlap with what physics majors take. However, there is overlap in some material here and there, like thermal physics and these thermodynamics classes, or the dynamics class and classical mechanics. A physics major again dives more into physics subfields and can take elective classes in particle physics, relativity, atmospheric physics, condensed matter physics, and plenty more, which engineers are not required to take. So now if you're still on the fence and just cannot pick, let's talk about your options. If you really want to study both, you could look into engineering physics. I don't currently have the major on the channel, but it's been a very common request. It's basically a combination of physics and engineering where you take classes in both disciplines. Many people who go into this major end up going to graduate school for either physics or engineering afterwards. But this is not a very common major, so be sure to make sure the schools you're applying for have it. Another option is you can take classes on the side that are not within your major. That could be for electives or maybe as a minor for those who go to schools that offer one. It's common to take like computer science classes along with a physics degree, or lots of engineers end up minoring in physics just to gain that extra knowledge. But one of the biggest questions I get is, can I go from a physics bachelor's to an engineering master's or even PhD, as well as vice versa? I always gave answers based on what I could find online, but for this video I decided to really figure it out. So I emailed about 20 of the more top tier schools saying either I want to get a master's in engineering but I have a bachelor's in physics, or vice versa. What are my options? And here's what I found out. In general, it seemed like going from a physics bachelor's to an engineering master's was a little easier to do, which I'll go over first. For example, an advisor from the aerospace engineering department at Purdue said, some of our current aerospace engineering grads come from math and physics, then mechanical, computer, and electrical engineering backgrounds. There were no specific prereqs, and you could do your catching up in the master's program. You just take the undergrad classes in the beginning. An advisor from the computer science department at the University of Washington sent a really helpful email and laid out how you don't need a computer science degree, but they do want you to have a background in these topics. So if you study physics in undergrad and want to do computer science in grad school, you should plan to take these courses on the side during your undergrad. Here's an email from a computer science advisor at the University of Illinois, one from a structural engineering advisor at UC San Diego, and one from a bioengineering advisor at Rice. I'm not going to go over those, but feel free to pause the video and read through them yourself. Now, if you want to go from an engineering bachelor's to a master's in physics, here's what I found. The most thorough email probably came from a Princeton advisor who said that, again, you don't need an undergrad degree in physics, but they do like seeing completed coursework in a lot of those typical undergrad physics classes. For people going to school in the US, a GRE general exam and GRE subject test in physics is required for a lot of these schools. The GRE general exam is like the SAT or ACT for grad school, as it covers multiple subjects. Then the physics GRE covers material from the first 3 years of undergrad physics specifically. So if you can take those classes somewhere or even self-study and do well, that'll improve your chances a lot. For those outside the US, they care much more about your grades and any research/experience you have in the field. Here's another email from a physics advisor at Cornell, one from Northwestern, and for those in Europe, I even sent an email to Cambridge if you want to read through that yourself. So if you want to do physics as a master's but are not doing it for undergrad, try to take several of their second and third year classes if possible. At my school, all engineers take these physics courses anyway. then if you can manage to take at least 4 of these core physics courses, and ideally a lab, which is pretty much what a minor is, you would be in a really good position if you keep your GPA high and score high on necessary exams. And if you study physics in undergrad but want to do, let's say, computer science in grad school, try getting a computer science minor or taking some of those key classes, ideally up through algorithms and theory of computation. For other engineering disciplines, at least try to take their second year classes, such as statics and dynamics, for example. As you'll see, the one thing that every single email had in common was that you don't have to have any specific degree before entering a master's program. They often pick candidates on a case-by-case basis and look at many factors. So just try to give yourself that extra boost by taking those extra classes, and you should be able to find something. All these advisors were very nice and happy to help, so of course reach out to schools of interest if you have any questions for them as well. Otherwise, that's it for this video. If you enjoyed, be sure to like and subscribe. Don't forget to follow me on Twitter and join the Major Prep Facebook group for updates on everything, and I'll see you all in the next video.